Hello, and welcome back to the web series Developing SPECTER using Innoslate's digital thread. My name is Mallory Jones, and I'm a systems engineer here at SPEC Innovations. In the previous videos, I introduced the Break the Ice Challenge, initiated the Lunar Rover project, and demonstrated Task 1, 2, and 3. In this 8th video of the web series, I will demonstrate the work conducted using Innoslate's integrations. This video will overview how GitHub, STK, MATLAB, and Ansys were used to build and test the SPECTER lunar rover prototype. Additional videos will be provided later to demonstrate how these tools were integrated with Innoslate. As mentioned briefly in the previous Task 2 web series video, 2 code repositories were cloned from those provided by the LEO rover prototype. One created the user interface, and the other sent and received commands between the UI and the LEO firmware. Both code repositories work together to control the SPECTER rover prototype. A token is granted per team member in order to access GitHub via Innoslate's GitHub view. The GitHub view in Innoslate displays all the lunar rover project's repositories on the GitHub dashboard and allows team members to collaborate on GitHub issues. A GitHub issue was created for each data recording to be collected by the hardware and each message to be displayed in the user interface. This included an issue for detecting obstacles in the front and rear of the rover body, calculating the distance obstacles are from the front and the rear of the rover body, displaying these two distances on the user interface, displaying an obstacle collision warning when an obstacle reaches 0.5 meters from the rover body, reading the voltage output of the prototype's battery, displaying live voltage output of the prototype's battery in the UI, and displaying the SPEC Innovations logo. SPEC software team then modified and cloned LEO rover repositories by writing code and publishing the updates to GitHub. A more detailed description of this process in Innoslate, including video demonstrations, will be recorded at a later date. During the Task 1 Design web series video, a travel route was mapped for the lunar rover prototype to follow during its mission. This was done using site coordinate locations and the distances between the sites. An analysis was performed on this travel route using AGI's Systems Toolkit. In STK, a model of the rover's travel route on the moon was created to calculate the time to navigate between the sites, as well as to calculate the estimated time to reach the mission's goal of collecting 10,000 kilograms of water. Several assumptions were made during the STK model development. This included the same rover route was followed for every regolith and excavation delivery cycle. The full-size rover has an excavation rate of 100 kilograms of regolith per hour. The full-size rover has a carrying capacity of 100 kilograms. The full-size rover can complete 10 excavation cycles before needing to be recharged. The battery takes 4 hours to complete one full charge. And unloading regolith from a storage container takes 15 minutes, and loading water into the storage container takes 1 hour. In STK, a model was built to represent the lunar rover's mission environment. To create the model, various objects in STK were used to represent the mission. These included the moon represented by a central body, the site locations distinguished and plotted using their latitude and longitude coordinates, the lunar rover represented by a ground vehicle object, and communication with Earth represented using a network of satellites. The fidelity of the STK model was increased by adding lunar terrain elevation, obstacles, and crater regions. This was done by following the maps provided by the Break the Ice Challenge and researching the Shackleton crater. After creating the STK model, an action diagram was developed in Innoslate to co-simulate the mission scenario with STK. This action diagram represents one full-size lunar rover excavating regolith from the surface, transporting the regolith to the water extraction plant, and delivering the water for long-term storage. The simulator was set to run until 10,000 kilograms of water is collected, or 365 Earth days have passed. Once the action diagram is created to model the lunar rover travel routes, scripts were added to the action entities in the diagram. These scripts communicated with STK model in order to initialize STK, create global variables for time to traverse values acquired in STK, calculate duration components such as start and end times, calculate velocity vector components using the duration components, and use duration components to calculate travel times between the lunar sites. A co-simulation with STK using Innoslate was then conducted in the action diagram. After executing either discrete event or Monte Carlo, the simulator calculated a total mission duration of 10.67 months to collect 10,000 kilograms of water using the previous assumptions. A total travel distance of 3,500 kilometers was also calculated that would be covered by the lunar rover during its mission. It is also predicted that a majority of the mission's lifetime will be dedicated to excavation and extraction processes. The results found during the Innoslate STK co-simulation were then verified using another co-simulation, this time with MATLAB. To conduct this co-simulation, velocity vectors and the x, y, and z planes were first retrieved from STK through Innoslate. Then they were inputted in a function script written in MATLAB. The MATLAB function calculated the magnitude of the lunar rover's velocity at any given moment in the mission. To conduct the second co-simulation with Innoslate, STK, and MATLAB, additional scripts were added to the same Innoslate action diagram that was executed previously. But this time, the scripts were added to initialize MATLAB in addition to STK. A total distance traveled resource entity was also added to the action diagram to compute the number of kilometers traveled by the rover during its mission on the moon. Finally, a MATLAB integration URL was applied to the simulator settings to access MATLAB APIs during model execution. After running the Innoslate action diagram in either the discrete event or Monte Carlo simulators, the same results during the first co-simulation were found. A GET request was used to retrieve the velocity vectors from the STK model to calculate a mission duration of 10.67 months and total distance traveled of 3,500 kilometers. A more detailed description of this process, including how to create this STK model, the action diagram, and the MATLAB function with its data settings, will be recorded at a later date. This will also be uploaded to the Rover series. Once the SPECTER prototype was completely built, testing was conducted as demonstrated in Task 2 and Task 3. To support verification testing, the Ansys platforms SpaceClaim and Static Structural were both used to analyze the excavator claw design and locate any design flaws. During the excavator claw design analysis, metrics were calculated by Ansys SpaceClaim and Ansys Static Structural. These prototype excavator claw metrics included surface area, volume, maximum load capacity, and maximum pressure tolerance. After this analysis, the results and metrics were inputted in the mission and excavation scenario models previously demonstrated in order to create higher fidelity simulations and results. First, a model of the excavator claw design was uploaded to Ansys SpaceClaim platform, and the excavator claw's CAD drawing was analyzed using the design engineering software. SpaceClaim calculated a surface area of 1.48 times 10 to the negative 2 meters squared, and a volume of 1.27 times 10 to the negative 4 meters cubed for the excavator claw. The density of regolith, 1,790 kilograms per meters cubed, and the volume value were inputted in the density equation to calculate the maximum load capacity the prototype excavator claw can support per dig during excavation. This maximum load mass was found to be 0.2279 kilograms of regolith per dig. The density of the regolith input in this equation was provided by the Break the Ice challenge. The excavator design analysis was continued using Ansys Static Structural to determine the pressure tolerance of the excavator claw. To do so, it cannot be assumed that the maximum load capacity will be utilized for each dig. Because of this important functionality, varying load capacities were found for the excavator claw at 80 and 60% of the maximum capacity. The pressure equation was then utilized with each varied load capacity of 0.182 kilograms at 80% and 0.136 kilograms at 60% to calculate the pressure tolerance that the excavator claw can endure during excavation. A pressure tolerance of 4.39 times 10 to the 3 pascals was calculated for 80% load capacity, and a pressure tolerance of 3.29 times 10 to the 3 pascals was calculated for 60% load capacity. Fixed support points in purple and impact areas in red were identified to mark where the excavator claw design will be affected during excavation. Once the excavator claw surface area, varying load capacities, pressure tolerances, and impact areas were calculated or identified, a structural analysis of the excavator design was performed in Ansys Static Structural. The structural analysis was conducted to determine the strength and stability of the excavator claw design under varying load conditions. A strain, stress, and deformation tests were conducted for both the 80 and 60% load capacities to locate potential design flaws. Ansys Static Structural results determined 100 million excavation cycles can be performed before any fatigue will impact the performance of the excavator claw. Knowing this time to failure enabled a more accurate and reliable maintenance schedule and plan. The Ansys results calculated for the Rover prototype's excavation claw design were then scaled up to the full-size Rover. This was done by comparing the mass of the prototype to an average full-size rover from the Apollo missions. This ratio is 5.4 kilograms to 108 kilograms, or 1 to 20. A pressure tolerance of 0.878 pascals for 80% load capacity and a pressure tolerance of 0.0659 pascals for 60% were calculated for the full-size rover. Since these calculations and the analysis were done on one excavator claw, the results were doubled to mimic the excavation subsystem utilizing 2 claws. Up next in the web series Developing SPECTER using Innoslate's digital thread is a video demonstrating the Rover prototype performance analysis. Thank you again for being here today, and I'll see you in the next video.